Hi everyone. In this lesson we're going to talk about doing analysis with conditionals. We've already looked at analysis with negations, ands, ors, and exclusive ors, so we're just adding in two new operations into the set of logical operations we've looked at so far. The two operations we're adding are the implies and the if and only if. And the first thing we looked at when it came to negation, and or and exclusive or was order of operations. So if we have a statement, in which order do we compute the operations first? It turns out that the implies and the if and only if are the last in the order of operations, and they occur on the same level. So if they're mixed together in a statement, you need to use parentheses to indicate which operation should be performed first. Let's look at an example. So let's say we're computing true or false implies not true. The first operation we would compute is the not, so we would perform not true. And here we have not true becomes false. Next, according to order of operations, we would do the or. So we have true or false implies false. Or comes next in order of operations, and true or false is true. That leaves us with true implies false, and true implies false equals false. So that's the answer, is true or false implies not true is false. Now let's look at some of the basic properties of implies and if and only if. So first of all, every statement implies itself, and every statement is logically equivalent to itself. In other words, every statement if and only if itself. So P implies P is always true, right? And P if and only if P is true, meaning P is logically equivalent to P. Also, if and only if is commutative, which means you can write the statements in either order. So P if and only if Q has the same value as Q if and only if P. They're equal. But implies is not commutative. So remember that true implies false is false, but false implies true is true. So you can't swap the order. True implies false doesn't equal false implies true. And therefore order does matter. So remember that. I think this is the first operation that we looked at in logic that is non-commutative. So you have to be careful with an implies. And neither of these are associative. So you always have to say which one comes first using parentheses, even if all the operations are the same. For example, if we do false implies true implies false, you need to indicate which implies comes first. If it's the first one, false implies true, well, false implies true is true, and then true implies false is false. So this would give you false. On the other hand, if we do the second implies first, true implies false is false, which is this, and then false implies false is true, because you can start with false statements and derive false conclusions. That's it, true. And so therefore, these things are not equal, and it does matter which order you put the parentheses. Or sorry, in which order you compute, which you indicate with parentheses. Now, we want to look at how if and only if and implies interact with these other operations that we've introduced before. And it turns out that P implies Q is actually equal to just saying not P or Q. So remember that the only thing that falsifies an implies statement is you can't start with true premises and get a false conclusion, at least if you're using good logic. So it's like saying P has got to be false, either not P, or Q's got to be true. So if Q is true, then false implies true, and true implies true. That's all true. So this is if Q is true. If P is false, then we're saying false implies true, or false implies false. I noticed that the statements true implies false is left out. So these are all true statements. So these is both equal true, and these both equal true. So that's sort of the idea behind P implies Q is equal to not P or Q. But of course you can verify it's always true with the truth table. So we're going to have our inputs over here, they're going to be all possible combinations of statements we could input for P and Q. So true and false, false and true, false and false. And then we do the computations. And so here's P implies Q, gives us true, false, true, true. And once you get down to the end, you'll have not P or Q is also true, false, true, true. So they're equal. These two things are equal. It's also the case that we could write P if and only if Q as P implies Q and Q implies P. And that was sort of the way I introduced it in the last video. And it logically works that way as well, even in formal logic. And if we wanted to, we could even write this as not P or Q and not Q or P. So we could even break this down so that we don't use an implies. It could be written completely in negations, conjunctions, and disjunctions. Now we're going to talk about a statement called a contrapositive statement, which is a very important statement in math. In fact, there's an entire proof technique called the proof by contrapositive, so which is essentially to prove a contrapositive statement of a statement you're wanting to prove. And it's the following. So if P then Q is equivalent to this statement, if not Q, then not P. And it's not the case that if P then Q is equivalent to if Q then P. You can't swap the order of Q and P. We talked about that above because implies is not commutative. But what we are claiming in logic is P implies Q is equal to not Q implies not P. So you can swap the order if you negate both statements. And we can actually just verify this algebraically. So now that we've shown a lot of identities using truth tables, we don't always have to go back to a truth table. It's one, kind of inconvenient, and two, they start getting really large. So let's just do an algebraic proof that P implies Q equals not Q implies not P. So P implies Q, we just showed, was not P or Q. And it's also the case that Q is equal to not Q. So here I'm saying that Q is equal to not Q. And that's why I have these two things equal, or basically I'm just replacing Q by not Q. Okay, and then to get from this line to this line, we're just going to swap the order. So remember that or is commutative, and I can write not P or not Q as not Q or not P. So I'm just reversing the order. And finally, I'm going to use the statement once again. Maybe it's easier to show you going up a line instead of down. So not Q implies not P. Remember that the implies here is equal to not the first statement or the second one. So it's equal to not the first statement or the second statement. And so this equality is how I'm getting from this line to this line. So not Q or not P is equal to not Q implies not P. And that verifies the proof that P implies Q is the same as not Q implies not P. Yes, so if and only if is transitive. It's another property of the if and only if operation. So if P if and only if Q, and Q if and only if R, then P if and only if R. You can kind of treat this as an equals. In fact, it is an equivalence relation. So if P equals Q and Q equals R, then P equals R. This is the picture you can have in the back of your mind. So to break this down, the English into logic, we get the following claim for any P, Q, and R. Sorry, this is to put this statement into pure logic. I couldn't remember what was going on with that statement. Right, so we're saying P if and only if Q and Q if and only if R implies P if and only if R. And so removing all the English and writing this in pure logic, we have the following statement here, which just replaces the words that I said with the logic symbols. So this is the and this is the implies. Okay, so just to do one last example of an algebraic manipulation, we're going to prove the claim P and Q implies R is equal to P implies R or Q implies R. So this is a distributive property. This this implies R is distributed. So this becomes an implies R, and this becomes an implies R. And when we distribute, it's in a sense similar to De Morgan's law. So remember that the operation flips. So this was an and it flips to an or whenever we distribute. So let's show that this works. And before we do this, we're going to go ahead and verify one other claim that's pretty easy, but we haven't shown it before. So let's go ahead and show that this is true. That claim is that P is equal to P or P. And so P could either be one of two values, right? It's either true, which gives us true equals true or true. That's true. And false equals false or false, which is also true, right? So false or false is false, and true or true is true. So we can replace any statement with the statement or itself because it's equal to the statement itself. Now let's do the algebraic manipulation. So we're going to start with P and Q implies R, and then use the fact that it's not the first statement or the second statement. So this becomes not P and Q or R. To get from here to here, we use De Morgan's law. So this negation distributes, it becomes not P or not Q, and then or R. And to get from this line to this line, we're going to use that statement we just said, that really simple statement that R equals R or R. So I replaced R by R or R. And the reason for that is we want two R's in the equation. So now we can drop the parentheses because everything's an or. So or is commutative and associative. That means whenever we have a whole bunch of ors, we can just drop all the parentheses. It's not P or not Q or R or R. And we can also rearrange the statements. So to get to this line, we're just rearranging the R's. It's not P or not Q or R. So I took the Q and the not Q and the R and swapped them. And finally, the last line just uses this fact that it's not the first statement or the second statement as an implies once again. So not P or R is just P implies R, and not Q or R is Q implies R. And that's where I needed the two R's. So now I have this implies R and this implies R. And that's what I wanted to show, was that P and Q implies R is equal to P implies R or Q implies R. It might not be completely clear how I got those steps, so I will say sometimes you have to work backwards on these things or try a few things. Whenever we write this in a book, of course, it comes out so nicely because we worked it out beforehand. But I've explained why each equality is true, and not necessarily how I thought through them. So there's a related lesson in set theory on the analysis with unions, intersections, and complements. So if you're interested in learning how this logic relates to sets, I would encourage you to go there and check out that lesson also.